Let us now find a relationship between Cp and Cv. Cp is heat capacity at constant pressure and Cv is heat capacity at constant volume. Now, in order to find the relation, we have to write either Cp or Cv in terms of associated heat change divided by the temperature. For Cp it is d cross q P by dt. For Cv it is d cross q V by dt. Now we can start from the first law using du is d cross q plus d cross w, and then we can impose some conditions where I will use the fact that du is nothing but Cv dt plus del u del v t dv, and similarly on the right hand side I can actually use the relationship for enthalpy which we just discovered. So we rewrite this equation as d cross q is nothing but du minus d cross w. Now du we are writing as Cv dt plus del u del v t dv plus d cross w. Now in order to get a relation between Cp and Cv, I have to write this d cross q P as Cp. So we are considering a constant pressure process. So at constant pressure, what will happen? I will have d cross q P is nothing but Cv dt plus del u del v t dv minus, now the expression for d cross w is minus P opposing into dv, but since it is a constant pressure process, P opposing is nothing but P, which is pressure of the system. So we can write it as minus P dv, and then we can divide both sides by T and define Cp as d cross q P divided by dt. So the right hand side becomes Cv plus del u del v t. Remember we are dividing by dt both sides. So before that we can take the dv factor common and write it as this, and since we divided both sides by dt at constant pressure, we can write that Cp is nothing but equal to Cv plus del u del v t minus P into del v del t P. Let me rewrite it once again, and then we will discuss what are the values of Cp minus Cv for different systems. So from here we are writing Cp minus Cv is del u del v t minus P into del v del t P. Now think about a solid. For solid, this term del v del t P, which is the change in volume with respect to temperature, keeping the pressure constant, that will be almost negligible. So Cp minus Cv for solids is almost 0. Now let us consider what will happen for an ideal gas. For an ideal gas, we have del u del v t is 0. Why? Because the internal energy is only a function of temperature for ideal gas, and Joule's experiment showed that there is no change in internal energy with respect to volume. So, if the first term gets 0, then what we are left with is Cp minus Cv is nothing but minus P into del V del Tp. Now, what is del V del Tp? At that point, we can use the ideal gas equation. We can write V as nRT by P. So, del V del Tp will be nothing but nR by P. So, this will be nR by P with a negative sign that makes the total thing as positive. So, this thing gets cancelled. So, Cp minus Cv is nothing but nR. If we consider in terms of 1 mole of substance, then instead of writing Cp and Cv, we can write them as Cp bar by Cv bar by dividing both sides by the number of moles. So, the molar heat capacities Cp bar and Cv bar are related as Cp bar minus Cv bar is R, or the molar gas constant for an ideal gas. Now, let us discuss what happens if we do a change of the system at constant pressure. We already discussed that we got a relation that the total derivative for the enthalpy is nothing but Cp dt plus del H del P T dP, and we are left with the task how to measure this del H del P T. For that, we will discuss something known as Joule-Thomson experiment, but before that, let us discuss what is the total derivative for enthalpy. Now, enthalpy was defined as U plus PV. So, the derivative dH is nothing but du plus PdV plus VdP. This, remember that this VdP will be 0, but only for if we consider a constant pressure process. Now, we can write this dH as Cp dt plus del H del P T dP, and similarly we can also write the equation for du, which was Cv dt plus del U del V T dt, sorry, del U del V T dV, plus we have P dV plus V dP. Now, consider a constant temperature process. If we have constant temperature, which means dt is 0, these two terms cancel, these two terms become 0. So, we have del H del P T dP is del U del V T dV plus P dV plus V dP. As before, we can divide both sides by dP, and keep in mind that we are doing it at constant temperature. So, this quantity del H del P T is expressed as, again before I divide both sides by dV, I can actually write these two terms as del U del V T plus P times dV. Now, we are taking a partial derivative with respect to pressure at constant temperature, plus if I divide by dP, this term becomes just V. So, now we get an expression for del H del P T for any system. Now let us consider how this quantity, what will be the value of this quantity for different system. Let us consider first an ideal gas. Now for an ideal gas, we know that internal energy is a function of temperature only. Now since H is nothing but U plus PV, which is U plus RT for an ideal gas, so this right hand side is always a function of temperature, because internal energy is a function of temperature and RT is of course depending on temperature. So del H del PT should be 0 because we are keeping the temperature constant. So internal energy will not change, RT will also be constant, so their differential will be 0. So del H del PT is 0 for an ideal gas. You could also get it by a different way. For an ideal gas, this term is 0 as we already discussed. Now you can carry out this quantity. You just write V in terms of the pressure, which will be nRT by P, and then you can calculate this derivative and you will find that the answer will be minus V. This minus V cancels with this plus V and you will also get 0 if you follow this equation. So either by following the logic that for ideal gas the internal energy is a function of temperature only, we get del H del PT equal to 0, or just following the formula also we can get it 0. Now for solids and liquids or for condensed phase, what about the value of this del V del PT? Remember what is del V del PT? It tells you the change in volume per change in unit pressure, keeping the temperature constant. Now solids and liquids are known as condensed phase, where the intermolecular interactions are much more compared to gaseous phase. So there the change in volume will be very little compared to pressure when we apply pressure. So this term we can almost ignore. So for solids and liquids, the value of del H del PT will be almost equal to V itself from this equation. Now let us try to understand what is the Joule-Thomson experiment. Now already we discussed for ideal gas del H del PT is 0. Similarly, we saw earlier that del U del VT is also 0, and there was an experiment which we called as Joule's experiment that also showed that del U del VT is 0. However, for real gases, del U del VT or del H del PT is not 0. Now you may ask this question, why then in Joule's experiment we did not get any finite value for del U del VT, which means actually why we did not see any drop in temperature. So the answer is that experiment was not one of the very refined experiment, meaning the gas Joule used was already so dilute that it was behaving ideally. When Joule and Thomson carried out another experiment which is known as Joule-Thomson experiment, they figured out that there is a small but finite change in that quantity del H del PT. So Joule-Thomson experiment discusses about measuring this quantity del H del PT experimentally. Now let us first describe what is the experiment. In this experiment, Joule and Thomson took a cell tube, and inside the cell tube there was a wall which is a perforated wall. What do you mean by that? It's a wall through which the gas molecules can pass from one side to the other side. In the original experiment, they took a wall made up of silk. So it's a fine orifice or sieve kind of wall where the gas can pass through. Now initially they put a piston here and they applied pressure on this piston. The pressure of the gas here was P1 and the volume was V1, and say the temperature was T1. The pressure and the temperature were simultaneously measured by a pressure gauge and a thermometer. Similarly, on the other side, initially the piston was kept here, very close to the wall. Now if you make a pressure from left to right, what will happen is that eventually this piston will move from its initial position to the wall, which is a fine orifice, and then the other piston will move to some distance because the gas molecules are passing through this fine orifice. So let us assume that the final pressure, volume and temperature are P2, V2, T2 for this chamber. Let us name this chamber as A and let us name this chamber as B. And for this chamber also there was a pressure gauge and a temperature and the thermometer which was measuring the temperature. So we divided the system into two parts, A and B, which were divided by a fine orifice or a piece of silk, and a piston moved from left to right, collapsing the system A and then increasing the volume for system B. That was the experiment. Now initially that means the volume of system B was 0, and also after the experiment was done, the volume of system A was 0. So if we want to write down what was the work done in this process, we can write the work done is nothing but the total work done is nothing but the work done on the left hand side, or we can just write it as WA, and work done for the chamber B together. Now what was the work done for the chamber which is we denoted as chamber A? So the expression for work done is minus P opposing into dV. Now what was P opposing in this case is P1, because remember as we increase as we move the piston from left to right with some pressure, the opposing pressure is always P1, because the gas molecules are leaving the chamber A and going to the chamber B, and as a result the piston which was here initially, the second piston, that keeps on moving. So the opposing pressure was P1 times dV, and the initial volume remember was V1, but the final volume was 0 for chamber 1. Similarly, for the work done in the other chamber, which is the chamber B, is nothing but P opposing into dV. In this case the P opposing has to be P2, because remember that the pressure was developed, the final pressure was P2, but it maintained the pressure so that the piston actually kept moving as we were trying to increase the pressure. So for this chamber it is P2 times dV. The initial volume was 0, the final volume was V2. Now we can easily rearrange it. It will rearrange to minus P1. This is there is a change in volume is minus V1. So we'll finally get P1 V1 minus P2 V2. Now the work done according to the first law can be written as change in internal energy plus the associated heat change. So remember the first law, delta U is Q plus W. So W is nothing but delta U minus Q. Now in this case Q is 0. Why? Because this entire tube was thermally insulated. So there was no heat exchange with the surrounding. So we can write, since U is a state function, delta U as U2 minus U1. Then we can arrange the terms. What we got? We got U2, and we can write this P2 V2 term together. U2 plus P2 V2 is nothing but equal to, we can take this U1 on the right hand side, U1 plus P1 V1. So what we got is that U plus PV is nothing but the enthalpy, which means H1 is equal to H2 in this process. So in Joule-Thomson experiment, the process is called isothalpic because the enthalpy of the system did not change. So what Joule and Thomson measured is the associated temperature drop, which is minus delta T, as a function of the associated drop in pressure at a constant enthalpy. So they defined a term which they called as mu Jt, which is known as the Joule-Thomson coefficient, and defined it at the change in temperature as a function of pressure for a constant enthalpic process, which was carried out in their or measured in their experiment. Now what will be the expression of del T del P H? Now remember, since it's a partial derivative of enthalpy, temperature with respect to pressure with keeping the enthalpy constant, we can just start with the equation of enthalpy, that dH is Cp dt plus del H del P T dP. Now what we have to show here is this term. So we can easily get it by taking a derivative del T del P, means actually we have to divide both sides by dP and somehow write this term as del T del P for constant enthalpy. If the enthalpy is constant, the left hand side becomes 0, and if we divide both sides by dP, we'll get Cp del T del P at constant enthalpy plus del H del P T. So we got a very interesting relationship. Del H del P T is nothing but minus Cp, because we are moving this term on the left hand side, and this term was already defined as mu Jt. So Joule and Thomson did this experiment where they measured mu Jt by measuring the change in temperature as a function of pressure, and they are measuring the temperature drop as a function of pressure drop, as is shown here. And Cp was of course known for a gas, and then if you measure mu Jt, then you can measure this quantity del H del Pt. So this del H del Pt was found to be small but a non-zero quantity for real gases. Similarly, if one does a very refined experiment, then one can also show that del U del Vt for real gases is actually non-zero. For ideal gas, either del H del Pt or del U del Vt both are 0. So far what we have discussed is as follows. We first discussed the statement of the first law and how the mechanical equivalence of work leads to the statement of first law as for any cyclic process, the work done must be equal to the heat withdrawn. From that we got a very interesting concept which we termed as the energy or the internal energy of the system. Then we considered the change in volume for a process, and we got a beautiful relation for the total differential of the internal energy, connecting it with Cv, the heat capacity at constant volume. Similarly, for a constant pressure process, we define another quantity H, which is U plus Pv, and just like the U or the internal energy, it was also a state function. And then we talked about the relationship between the total differential dH connecting it to Cp, which is heat capacity at constant pressure. Then using those relations, we got a relationship between Cp and Cv. What is the difference between heat capacity at constant pressure minus heat capacity at constant volume? We found for ideal gases, for 1 mole of ideal gas, this will be the difference will be nothing but equal to the molar gas constant. And then we proceeded and tried to figure out what is the value of this quantity del H del Pt for a real gas. For that we described what is known as Joule-Thomson experiment, which was basically carried out for a sealed tube which is thermally isolated, and which is divided, the two portions of the tube are divided as A and B by a fine orifice, or in this original experiment they used a piece of silk. And then we discussed how movement of the piston from one side moves the piston on the other side, and then how the associated drop in temperature and pressure can be measured to define a quantity which we called as Joule-Thomson coefficient. And then if one measure the Joule-Thomson coefficient experimentally, which Joule and Thomson did in their experiment, then one can also measure del H del Pt, which is small for real gases. Similarly, one could also measure del U del Pt using Joule's experiment, although Joule did not find any noticeable change in temperature, but later on people found by refined experiment that del U del Vt is also non-zero for real gases.